Hello everyone, welcome to our channel's Ultimate Science Academy. Now we discuss force and torque in physics in this video. We'll discuss some important topics in this video. First we discuss force, translatory equilibrium, springs, friction, the basic or fundamental forces, and also we discuss impulse and torque. Now, what is the force? Force is a push or pull which tries to change or changes the state of rest or of uniform motions. That is, force is a case of translatory motion. It arises from the interactions of bodies either due to contact or from a distance. For example, gravitational or electric forces between two charged particles. Here we discuss body at rest. Now in figure first, we see if body remains at rest, force is trying to change the state of rest. This shows in this figure. And now we see if body moves, force is changing the state of rest. Next, we see body in motion. When force is parallel or anti-parallel to motion, it changes the magnitude and not the direction of motion. Here we see magnitude increase and here we see magnitude decrease. Now next we see when force is always perpendicular to motion, in which direction of motion only changes, not the magnitude, and motion is uniform circular. Here next in figure 4th we see both magnitude and directions of motion changes and motion is non-uniform, circular, elliptic, parabolic or hyperbolic. Here this is the condition when force acts at an angle to the motion. Now when force changes the state of rest or motion of a body by Newton's second law, here we see F factor is equal to dp vector over dt. F factor is equal to d over d mv vector over dt. Here now we can also write this. Now for body as mass, m is equal to constant, dm by dt is equal to 0. So formula is F factor is equal to m a. F factor is equal to m a vector. In physics, we also have situations in which mass of a body changes when velocity of escape of mass is constant. In such situations, as v vector is equal to constant is equal to 0, it is reduces to F vector is equal to v vector dm by dt. Further, in case of a conservative fields, F factor is equal to minus gradient of u. If potential energy u is assumed to be a function of position r only, the above result can be written as F is equal to minus du by dr. This is a mistake in this video. This is only the F, not F factor. So F is equal to minus du by dr is equal to minus slope of u by r curve. Some important points also has it also a polar vector, and F force has dimensions. Is dimension is ml t minus 2. Some important points are it is a polar vector, it has dimensions, it has units. Next, when force is written without directions, then positive means repulsive while negative means attractive, as shown in figure 5th. For example, two similarly charged particles, electric force is positive, meaning repulsive, while between dissimilar charged particles is negative, means attractive. Next, force can be applied by muscles, machines, or natures. When force is applied by muscles and machines, there is an upper limit to it. This limit is different for different muscles and machines. Art of next, art of some many natural forces for distance is equal to 10 to the power minus 15 meter. Nuclear force is the strongest, while the gravitational force weakest. Next, all the forces according to their dependence on positions or motions can be divided into the following four types. First, constant force. Second, time dependent force. Third, position dependent force. Fourth, velocity dependent force. First, constant force is if the directions and magnitude of a force is constant, it is said to be a constant force. Mechanical forces of constant magnitude are produced by machines. Tension in a string can also be a constant force. Next, time dependent force. If a force depends on the time, it has to be a time dependent. For example, in case of impulse or motion of a charged particles in an alternative electric field, force is time dependent. Next, position dependent force. If a force acting on a body depends on the position of a body, it's said to be position dependent force. Gravitational force between two bodies or force between two charged particles are example of a position dependent forces. Next, velocity dependent force. If a force acting on a body depends on the velocity of a body, it's said to be velocity dependent force. Viscous forces and force on a charged particle in a magnetic field are velocity dependent force. Next, we also see a position dependent force. We also see position dependent force is always directed towards or away from a fixed point and said to be central, otherwise non-central. The motion of a earth around the sun, motion of an electron in an atom, or scattering of alpha particle from a nucleus are some few examples of central forces. And in the case of a central force, as force passes through a fixed point, torque about the fixed point is always zero, and so angular momentum is conserved. That is in case of a central force. So torque is equal to zero and angular momentum is equal to constant. Next, force can also be classified as conservative and non-conservative. In under of action of a force, work done in a round trip is zero, or work is path independent, the force is said to be conservative, otherwise not. Gravitational, electric, and elastic forces are conservative, while frictional and viscous forces are non-conservative. In presence of a non-conservative force, there is a loss of mechanical energy, while it is usually converted into heat. Next, force can be classified as internal and external. Internal forces are those which arises from the interactions with the other particles that are part of a system, while external forces are those which originate beyond the system under considerations. Same forces can be external or internal depending on the system. If we consider a body as a system, the force of gravity of Earth is external, while if we consider the body and the Earth as a system, the force becomes internal. Total internal forces acting on a system is always zero, as these are part of action, reaction pairs, and cancel. So next, force can also be classified according to its origin, such as reaction, thrust, tension, elastic, etc. Next, if a number of forces are acting on a body, we find the resultant force using law of parallelogram of additions, or we can resolve the forces as, that is, F vector is equal to F1 vector plus F2 vector, and so on. We also say accelerations acceleration of a body using Newton's second law. F vector is equal to m a vector. So we also find accelerations and velocity by this formula. So now what is translatory equilibrium? When several forces act on a body simultaneously in such a way that the resultant force on a body is zero, that is F vector is equal to zero, with F vector is equal to summation of Fi vector. The body is said to be in a translatory equilibrium. Some important points are: first, if a vector is zero, all its component must vanishes, and that is in equilibrium, F vector is equal to summation of Fi vector is equal to zero. Then summation of Fx is equal to zero, summation of Fy is equal to zero, summation of Fz is equal to zero. So in equilibrium, forces along x-axis must balance each other, and same is true for other directions. Second, as for a body, F vector is equal to 0, means ma vector is equal to 0, and dv vector upon dt is equal to 0, and so v vector is equal to constant or 0. That is, if a body is in translatory equilibrium, it will be either at rest or in uniform motion. If it is at rest, the equilibrium is called static, otherwise dynamic. Third, if the forces are conservative, then as for conservative force, F is equal to minus du by dr, or for equilibrium, F is equal to 0. That is, du by dr is equal to 0. That is, in conservative field, at equilibrium potential energy is optimum. That is, in equilibrium potential energy is maximum or minimum or constant. Now we discuss static equilibrium. The static equilibrium can be divided into following three types. First, stable equilibrium. Second, unstable equilibrium. Third है neutral equilibrium. First, stable equilibrium. If on slight displacement from equilibrium position or equilibrium position, a body has tendency to regain its original position, it is said to be in stable equilibrium. In case of a stable equilibrium, potential energy is minimum, and so center of gravity is lowest. Shown in this figure, this figure 6 depicts some examples of stable equilibrium. Second, unstable equilibrium. This shown in figure 7. If on slight displacement from equilibrium position, a body moves in a direction of displacement, the equilibrium is said to be unstable. In these situations, potential energy of the body is maximum, and so center of gravity is highest. This shown here some examples of unstable equilibrium. Now neutral equilibrium is shown in figure 8. If on If on slight displacement from equilibrium positions, a body has no tendency to come back to its original position or move in a direction of displacement, it is said to be in neutral equilibrium. In this situation, potential energy of a body is constant, and so center of gravity remains at constant height. Repeat here. These are some examples of neutral equilibrium. Now we will also discuss the stable equilibrium, lesser the potential energy or lower the center of gravity. That is, greater the base area, more stable is the equilibrium. This shown in this figure 9. Here if we plot graph F versus R and U versus R, at equilibrium F will be 0 while U will be maximum or minimum or constant. Here first we see in figure in graph A and in graph B. So U is equal to maximum, that is d square U over dr square is equal to positive and equilibrium is stable. Here U is equal to maximum, d square U over dr square is equal to negative, equilibrium is unstable. If U is equal to constant, d square U over dr square is equal to 0, equilibrium is neutral. This shown in this figure strength. While dealing with force problems where strings are involved, some important points to be remembered that first, strings is assumed to be inextensible. This is why the magnitude of oscillations of any any number of masses connected through string is always same. If the string is extensible, the acceleration of different masses connected through it will be different until the string can stretch. This shown in this figure 12th. Sorry, this shown in this figure 11th. Now, string is assumed to be massless unless stated. This is why the tension in its everywhere remains the same and equal to applied force. However, if a string has a mass, tension at different points will be different, being maximum is equal to applied force at the end through which force is applied and minimum at the other end connected to a body. Next, in order to produce tension in a string, two equal and opposite stretching forces must be applied. The tensions thus produced is equal in magnitude to either applied forces. This shown in this figure. That is T is equal to F and is directed toward inwards opposite to F. Here it must be noted that a string can never be compressed like a spring. Next, average strings can bear a maximum tensions, that is, if the tension in a string is continuously increased, it will break. If the tension is increased beyond a certain limit, the maximum tension which a string can bear without breaking is called the breaking strength. It is finite for a string and depend on its material and dimensions. Next, when a string is fixed horizontally and loaded at the middle for equilibrium of points P. This is point P here. This shown in this figure A. Figure 13, part A. Here it is clear that as 2t cos theta is equal to W, t is equal to W by 2 cos theta. So as length of a string is shortened, theta will increase, and so cos theta will decreases, and his tension in the string will increases. That is why a string loaded at the middle may break if the length of the string is shortened. Next, we see here in figure B, as t is equal to W over 2 cos of theta. So tension in the string will be greater, equal or lesser than load W, as cos theta is lesser, equal or greater than 1 by 2. That is, theta is greater, equal or lesser than 60 degree or pi by 2 radian. So this tension in the string can be lesser, equal or greater than load depending on theta. Next, we also see that tension in the string will be minimum when cos theta is equal to maximum is equal to 1, theta is equal to 0 degree. So T minimum is equal to W by 2. This is why tension in the string loaded at the middle can never be lesser than half this suspended load. Next, we also see here tension in the string will be maximum when cos theta is equal to minimum is equal to 0. That is, theta is equal to 90 degree, and then T maximum is equal to infinity. However, as every string can bear a maximum finite tensions, this situation cannot be released practically. Furthermore, as theta is equal to 90 degree means that the string is horizontal. Is shown in this figure. In figure C, we conclude that a string can never remain horizontal when loaded at the middle. However, greater the tension B or tension required to completely strengthen a rope horizontally is infinite. When a mass is suspended from vertical string in a carriage, following situations are possible. First, if the carriage, say lift, is in translator equilibrium, the forces acting on the systems are shown in this figure A. For translatory equilibrium at point O, R is equal to T naught, and for equilibrium of mass M at P, T naught is equal to mg. So in this situation, R is equal to T naught is equal to mg. Second B, if the carriage is accelerated up, the mass m is not in equilibrium, but it has shown as an upward acceleration A. So the upward force T must be greater than the downward force mg, such that T minus mg is equal to ma. So T is equal to mg plus ma. That is, tension in the string will be more than T naught, and then string may break if acceleration is such that T greater than breaking strength. Next, in C figure, if the carriage is accelerated down, the mass m is not in equilibrium, but it has a downward acceleration A. So downward force mg must be greater than upward tension T, such that mg minus T is equal to ma. T is equal to mg minus A. That is, tension in the string will be lesser than T naught. It is also interesting to note here that if the carriage begins to fall freely, that is A is equal to Z, tension in the string becomes 0. Next, We see here in this figure, if the carriage is accelerated horizontally, the motion of a point O will be accelerated translatory, while due to inertia, mass at P will try to maintain its position. So relative to P, O will move in the direction of acceleration, or relative to O, P will move in a direction opposite to accelerations. We usually represent this fact by the stating that mass m experiences a pseudo force ma opposite to acceleration. So as a result of this, the string will incline to the vertical in a direction opposite to the acceleration of a carriage. Now, as the mass m is in equilibrium inside the carriage, so t sin theta is equal to m c t sin theta is equal to ma, t cos theta is equal to mg. By solving this, we see tangent theta is equal to a by g, t is equal to m root of g square plus a square. So that is, tension in the string becomes more than T naught, and so the string may break. Also, the string does not remain vertical but inclines to the vertical at an angle theta equal to tangent inverse A by G opposite to the acceleration. Now these are the some formulas we discuss here. Now next we see tension in a string passing over a fixed pulley and loaded at the two ends such as Atwood machines is shown in this figure. Figure A. This is figure A, this is figure B. To understand this whole concept of the system shown in this figure, the force 7g Newton will pull the string down while 3g Newton on the other side will oppose it. So net pulling force is equal to 7g minus 3g is equal to 4g Newton, while the mass in motion while the mass in motion is 7 plus my 3 is equal to 10 kg. So magnitude of acceleration of A or B is equal to F by M, 0.4 gram meter per second square. So as for A, now as A is accelerated down while B up, so tension TA less than 7g Newton and TB greater than 3g Newton. So as tension increases when body is accelerated up and decreases when accelerated down, but as tension in the string must be same everywhere. So T must be greater than 3g Newton and less than 7g Newton. However, if we consider motion of B, TB is equal to mg plus में A is equal to 3g plus में 0.4g is equal to 4.2 gram Newton. And if we consider the motion of A, T is equal to m g minus A is equal to 7 bracket में g minus 0.4 g is equal to 4.2 gram Newton. From this it is clear that both A and B yield the same tension 4.2 gram Newton, that is 4.2 kg, which is more than 3 kg and less than 7 kg. Now we discuss springs. Springs can be many types such as helical, spirals, and are stretchable or compressible. Some important points are springs are assumed to be massless. It is said that this is why restoring elastic force in a spring is assumed to be the same everywhere. Spring can be stretched or compressed and stretch or compression is always taken to be positive. They show in this figure 17, stretch and compression. To produce extension or compression in a string, two equal and opposite forces are to be applied, and in equilibrium storing force developed due to the elasticity of spring is equal to either force, that is F is equal to F dash, and is always opposite to applied force. Next, force small stretch or compression. Springs obeys Hooke's law, that is for a springs force proportional to stretch or compression, F is equal to Ky, that is storing force is linear. This force in a spring is not constant and depend on stretch or compression Y. Greater the stretch, greater will be the force. Next, K is called, this is K. K is called the force constant of the spring and is equal to the slope of the force versus stretch curve. It has dimensions mlt minus 2 and unit Newton per meter. Greater the force constant of a spring, lesser will be the stretch for a given force, and more stiffer is said to be with the spring. The force constant K of a spring depends on the wire length, radius, and material used to make the spring. Radius of a spring R, length L of a spring. It is well established that for a given spring K proportional to 1 by L. That is, smaller the length of a spring, greater will be the force constant. Force constant of a composite springs. If a number of springs are connected to a body and we want to reduce it to a single spring, forming three cases of the common interests are possible. First, springs in parallel. Second, springs in series. Third, springs in series with a mass between them. First, this when spring in parallel, the situation is shown in this figure 20. First, we see in figure A. The situations is if the force F pulls the mass m by y, the stretch in each spring will be y. That is y1 is equal to y2 is equal to y. Now as for spring F is equal to ky, and as k dash are k not equal, so F1 is equal to not equal to F2, but for equilibrium F is equal to k F2 F1 plus F2, that is ky is equal to k1 y1 plus k2 y2. So we also see k is equal to k1 plus k2 and so on. But in series is shown in this figure B. As springs are massless, so force in this must be same. That is F1 is equal to F2 is equal to F. Now as F is equal to ky and as k dash are not equal, so stretches will not be equal. Y1 is not equal to y2. So y is equal to y1, but y is equal to y1 plus y2. So that's why F by K is equal to F1 by K1 plus F2 by K2. So this equation is reduced by 1 by K is equal to 1 by K1 plus 1 by K2 and so on. When springs in series with mass between them. If force F stretches a spring by Y, the other will be compressed by the same amount. So Y1 is equal to Y2 is equal to Y. Now as F is equal to Ky, K dash are not equal. So F1 equal to not equal to F2. But F is equal to F1 plus F2. So Ky is equal to K1 Y1 plus K2 Y2. So this equation also written as K is equal to K1 plus K2. Next, when a spring is stretched, work done on it is stored as elastic potential energy. If at any time a spring is stretched by an amount x, the force acting on it F is equal to Kx. So the work done in changing this stretch from x to x plus x dx. So dw is equal to F dx is equal to Kx dx. So work done in stretching the spring from 0 to y is W is equal to integration of 0 to y Kx dx. So is equal to half of Ky square. So elastic potential energy you store in the spring is U is equal to W is equal to half of Ky square. So that is work done or elastic potential energy stored in a spring where is known linearly with stretch. From it is clear that if the stretch in a spring is doubled, the force is doubled, but the energy stored becomes force time. Energy becomes stored becomes 4 times. If there are two springs of force constant K1 and K2 with K1 greater than K2, then work done. First, when they are stretched by the same amount, W1 greater than W2. This is here is. Second, when they are stretched by same force, then W1 less than W2. So work done is more in spring of smaller force constant. Next, elongation or compression produced in a spring. When a body is placed on its an equilibrium is achieved. If the spring is stretched by x, then in equilibrium mg is equal to kx or x is equal to mg by k. Next, when a body is just dropped on it, here see, due to the change in momentum on collision as impulsive force will act. So here F greater than mg if y is maximum stretch of a spring by conservation of mechanical energy is half of ky square is equal to mgy. So y is equal to 2 mg by k is called equal to 2x. That is when a body is just dropped on a spring, the maximum stretch is double of when the body rests on it in equilibrium. Next, when a body is dropped from a height h, then if the spring is compressed by z, potential energy lost by the body is mg h plus में z, while elastic energy stored in the spring is half of k z square. So by conservation of mechanical energies, half of k z square is equal to mg s plus में z. Here we see z is equal to mg by k bracket of 1 plus में root of 1 plus में 2hk by mg. Next, if a spring is horizontal and a mass m is attached to it, this shown in this figure, in equilibrium it is unstretched or uncompressed, and so its length will be equal to its natural length as mg is balanced by reaction r. However, if the system is made vertical as shown in this figure b, figure this and this, and then in equilibrium as is length l dash greater or less than l, such that mg is equal to k y naught. So this is also why in some problem related to the spring, sometimes we replace m by k by y naught by g, which is constant for a given mass and springs. What is friction? If we slide or try to If we consider a body on an inclined plane which is just on the verge of sliding, as shown in figure before, for equilibrium along and be perpendicular to the plane. Here we see Fr is equal to mg sine of theta and R is equal to mg cos of theta. Fr is equal to mu s r and mg sine theta is equal to mu s mg cos of theta. So mu s is equal to tangent of theta. So angle theta is called the angle of friction and angle of repose. In practical, it is usually found that mu s greater than 0 and less than 1. Next, it has been observed that the force of friction is practically independent of microscopic area of surface in contact and relative velocity between them. However, it depends on the nature of material of the surface in contact and their roughness and smoothness. Normally, with increase in the smoothness, friction decreases. However, if the surfaces are made too smooth by polishing and cleaning, the bonding force of adhesions will increase, and so the frictions will increase, resulting in cold welding. Next, friction is a non-conservative force, that is, work done against friction is path independent, and in its presence, mechanical energy is not conserved as it converts energy of motions of a body into heat. So friction reduces efficiency of a machine. Next, motion of a two bodies, one resting on the other, can be dealt easily using properties of friction and equations of motion. To understand this all, consider the following two cases. First, when force applied on the upper body. Second, when the force applied to lower body. First, when body A of a mass m is resting on a body B of mass m, and a force F is applied to the upper body as shown in this figure. Following three situations are possible. First, when there is no friction, the body A will move on a body B with acceleration F by m, and body B will remain at rest. So, this formula is A is equal to F by m while AB is equal to 0. Second, if friction is present between A and B only, the body A will not slide on B till FL less than FL, F less than FL, that is F less than mu s mg. So both will move together with common acceleration. Now A AA is equal to AB is equal to F by m plus में small m. So F dash is equal to MA is equal to MF over m plus में small m. Third, in a case of when the two bodies will move in the same directions but different acceleration, here force of friction mu k mg will opposes the motion of A while will case the motion of B. So the equation of motion of a body BA will be F minus Fk is equal to MAA. So now here we see AA is equal to F minus mu kmg over M and AB is equal to mu kmg over M. Next, we see when a body A of a mass M is resting on a body B of a mass M and a force F is applied to the lower body as shown in this figure. Again, there are three possibilities. First, when there is no frictions, B will move with acceleration F by M and while A will remain at rest. So, this formula is here. A is equal to F by M. Second condition, if friction is present between A and B only and both are moving together, then formula is A is equal to F by M plus small m. So, force on a body A will be F dash is equal to MF over M plus small m. So now as this force to the upper body A is provided by the friction between A and B, so both will move together only and only if F dash less than FL. So F less than mu s m plus m small m g. So both bodies will move together with accelerations AA is equal to AB is equal to F over m plus m small m. Third, from case B, it is clear that both will move with both different accelerations. But if F greater than mu s m plus m g, then equation of motion of A will be m A is equal to mu k mg. So AB is equal to F minus mu k mg over m. So for point B, F minus Fk is equal to MAB. So this is the formula. Now we discuss some basics of fundamental forces. All the observed forces in nature such as muscular force, tension, reaction, friction, elastic weight, electric, magnetic or nuclear can be explained in terms of only the following four basic interactions. These are gravitational force, electromagnetic force, nuclear force, and weak force. So, what is gravitational force? This is the force of interaction which exists between two particles due to their masses called the gravitational force. The force is given by the well-known Newton laws of gravitation. So, this formula is this. Second, electromagnetic force exerted by the one particle on the other because of the electric charges of a particle is called the electromagnetic force. That is, the description of the electromagnetic force is more complicated, but by the Lorentz force equations, this this formula is this. Next, nuclear force. Nuclear force is the strongest force that keeps nucleons together inside the nucleus in spite of large electric repulsions between protons. Radioactivity, fission, fusion, etc. result because of the nuclear force. Next, weak force is it acts between two elementary particles. Under its action, a neutron can change into a proton emitting an electron and a particle is called the antineutrino. This process is called the negative beta decay. Never think that a neutron is composed of a proton, an electron, and antineutrino. The force responsible for this change and many other radioactive decay reaction is different from gravitational, electromagnetic, nuclear force. Such forces is called the weak forces. The range of weak forces is very small, in fact much smaller than the size of a proton or a neutron. It has been found that two protons at a distance of 1 Fermi. So this is at a distance of 1 Fermi. This is the range force of weak force, electromagnetic, neutrons. This ratio is this. So weak force and electromagnetic force are different aspects of a single electro weak force. So these are the some basics of fundamental forces. Now what is impulse? If a large force acts on a body or a particle for a small time, the product of a force with time is called defined as impulse. This impulse. This formula is J vector is equal to integration of T1 T2 F vector dt. Some important points are it is a vector quantity having dimension mlt minus 1 and unit Newton second and its direction is same as that of force. Second, it is clear that the impulse is equal to the area under ft curve. This shown in this figure. Next, in case of impulse, usually force is time dependent. So if FAV is the average magnitude of force, we can write the magnitude of impulse as this is J is equal to integration of T1 T2 F dt is equal to F average of delta T. So in which delta T is the durations of for which the force act. The value of the F average must be taken so that the area within the rectangle, this shown in this figure, is equal to the area under the ft curve. So F average is equal to J by delta T. Next, according to the second law of motions, Newton's second law of motions is this: F vector is equal to dp vector upon by dt. So J vector is equal to p2 minus p1 is equal to delta p. So that is the action of impulse is to change the momentum of a body or a particle. The impulse of a force is equal to the change in momentum. This statement is also known as the impulse momentum theorem and is analogous to work energy theorem with the difference that the former is related to the vector physical quantity while the latter to scalars. Next, example of impulse are hitting, kicking, catching, jumping, etc. like this. And in all these cases, the impulse acts. Now the effect is F average equal to constant over delta T. So if T of a contact delta T is increases, average force is decreases and vice versa. So these are the examples of impulse. What is torque? If a pivoted, hinged, or suspended body tends to rotate under the action of a force, it is said to be acted on by torque. This shown in this figure, ABC. Some important points are it has dimensions ml2, t minus 2, and units in Newton meter, same as that of a work energies. It is an axial vector next, and its direction is always perpendicular to the plane containing vector r vector and the f vector in the accordance with right hand screw rules. It is compulsory to ascribe a positive sign to all torque acting to turn a body anti-clockwise and a minus to all torque tending to turn it clockwise. Next, the magnitude of torque will be tau is equal to Rf sine of theta. This is shown in this figure. So, tau is equal to Pf is equal to moment of force. This is why torque is synonyms with moment of force and P is called moment. So, tau tau will be minimum and maximum when sine theta is equal to minimum is equal to 0 degree, theta is equal to 0 degree. So F vector is collinear with R vector. So tau minimum is equal to 0. When sine theta is equal to maximum is equal to 1, theta is equal to 90 degree, F vector is orthogonal to R vector. So tau maximum is equal to Fr. Next, torque is the case of a rotatory motion, and in rotational motion it plays the same role as force plays in a translatory motion. Torque is rotational analogy of force. Some important formulas are in the rotation motions and in translatory motions are tau vector is equal to IA vector, I alpha vector, and F vector is equal to MA vector. So tau vector is equal to DL vector over dt, F vector is equal to dP vector over dt. So these are the some formulas in which a body is said to be in a rotational equilibrium if resultant torque acting on it is zero. So summation of tau vector is equal to zero. So for example, in case of a beam balance seesaw, the system will be in rotational equilibrium if tau 1 vector is equal to tau 2 vector is equal to zero. So this shown in this figure is like F1 L1 minus F2 L2 is equal to zero. So F1 L1 is equal to F2 L2. So, however, if tau 1 greater than tau 2, left hand side will move downwards, and if tau 1 less than tau 2, right hand side will move downward, and in the system will not be in a rotational equilibrium. Thank you so much for watching this video. Please subscribe, like, and also press bell icon button.